So, okay, I see we're live. Everything is on.
Welcome everyone to Progress in Prospecting Biology Special Lecture Series. Today is the 11th lecture of this series, and for this lecture we have with us Professor Bernard Patton. As always, you can post your questions during the lecture in the YouTube chat box, and there will be a moderator at the end of the session. And to introduce our speaker, we are pleased to invite Professor Inari Banerjee, our convener of this lecture series. Professor Inari Banerjee is currently heading the Immunobiology and Regenerative Medical Research Lab and the Transcription Outcome Research Unit at the Department of Zoology, University of Kolkata. Welcome.
Thank you, Krishnamurthy. A very warm welcome to all our viewers who have been with us for the last 6 months of progress and prospects in biology, where we try to bring to you what is happening around the world in biology. And on Saturdays, we have a special lecture series where tonight we are so honored to have with us Professor Bernard Patton, who does not need any introduction. However, I would introduce you to him, and then I would invite Professor Shantanu Rai, who has worked directly with Professor Patton, to say a few words, and then we will go directly to you, Professor Patton, and onto your talk. So very warm welcome to our viewers who are seeing this on YouTube and who would be seeing the talk doubtless that would be archived for later on. So to our live audience as well as to our audience who will be tuning in the future, warm welcome from the team of Progress and Prospects in Biology. And I introduce Professor Patton as follows. Professor Bernard C. Patton is Emeritus Professor of Ecology at the University of Georgia, USA. He's a systems ecologist and ecological modeler, interested in the application of mathematical system theory to ecology. He and his colleagues have formulated a system theory of environment called environment theory and analysis that pioneers the use of network mathematics to represent and analyze ecosystem networks such as food webs and biogeochemical cycles. His research publications include over 200 papers on a variety of ecological topics spanning marine, freshwater, and wetland ecosystems. During 1975 to 86, Dr. Patton was principal investigator of an NSF-sponsored ecosystem study of Okefenokee Swamp, Georgia. From 1978 to 88, he served as a member of EPA's Science Advisory Board. He chaired SCOPE ICSU's Scientific Advisory Committee on Wetlands, produced a two-volume review of the world's wetlands. He served as president of the International Society for Ecological Modeling, North America, from 1982 to 90. He is founder and president of Ecology Simulations Incorporated, which now inactive, has 4 months conducted research for the United Nations Development Programme, International Atomic Energy Agency, U.S. Soil Conservation Service, and U.S. National Oceanic and Atmospheric Administration. Dr. Patton has lectured and given short courses in systems ecology nationally and internationally. He has been a distinguished visiting professor and served on the editorial boards of several respected scientific journals. His edited works include the four-volume book series Systems Analysis and Simulation in Ecology, two volumes on wetlands and shallow continental water bodies, and Complex Ecology, the part-whole relation in ecosystems. A monograph, Hollow Ecology, the Unification of Nature by Network Indirect Effects, is currently in preparation. In 2006, he was awarded the Prigogine Medal of Siena University and the Wessex Institute of Technology. And just for students out here, he has a bachelor's degree from Cornell University in zoology, two postgraduate degrees, one from Rutgers University in botany and one from University of Michigan in zoology. And he did his PhD in botany, although I must say that it is, uh, he's so big and he's such a legend that reading out his bio sketch itself is an honor. May I invite Professor Shantanu Rai to say a few words, and then we will have our speaker set the mood for tonight's talk. Shantanuda, if you could please introduce Professor Patton, and we will start tonight's lecture.
So regarding his subject, I have that not guts to say something about Professor Patton. He is a legendary ecologist for the all time, and other than ecology, I can say him as a human being. He's a nice human being, and I considered him as one of my good mentor in my life, and he's a philosopher guide also. Not only me, he's a philosopher guide of all students, because I know he has produced many students. Whatever he told me, he produced almost 44 students. I think whenever he came here during 2014 in Shantiniketan, he told me that he has produced 44 students. Out of these 44, two students are president of different US universities, and one student, Thomas Pin, is a chair professor of MIT, maybe. He's a Thomas Pin, and in ecology, those who are working on ecological network analysis, that is Pin cycling index is a very common index in ecological science. And he produced a lot of good students, and they are well placed. And he told all of the students, whatever he produced, they are placed in very good areas in different institute, universities, even EPA, and everywhere throughout the world, I think so. And I think I considered him, he's a good philosopher, and his life is philosophy. And what at this age, I'm really surprised to see he is last October, I met him in Austria, Salzburg, and during that time, he told me, Shantanu, I need 15 more months to be 90 years old. And I think he is just 90. And I always considered him at the 90, he's a young boy at 90 years old. So yeah, I cannot walk with him. He is so fast, and his mind is like a 16 years boy. Okay, and regarding academics, I do not say anything about him. I have not guts to say something about Professor Patton, and I'm really very pleased to see him again live. And just I'm requesting Professor Patton to start his lecture. I think everyone waiting for listening his lecture, and I think so. It is my pleasure to say him to start your lecture. Thank you.
Shall I say a few words just by introduction?
Yes, please.
Yes, please.
And then,
yes, please. I can be speaking now. Yes. So I cannot see everybody out there, but I understand there are people out there. I would like to remind you we live in a very interesting time, don't we? And this is part of that interesting time. Here I am half a world away in a fairly early morning here, and it's getting on to late evening there. I'm very pleased to be here. I would like to say a few words to introduce the lecture that you will see a video of, and remind you that what I'm representing, my field, which is holistic ecology, which we shorten to the word holoecology. And holoecology is an attempt to bring systems thinking, system theory, and holism into the dominant ecology of today, empirical ecology. Ecology is scheduled to become, I think, one of the most important sciences in humanity, because it's endeavoring to deal with the complexities of all of nature. And all of nature taken at the biospheric level means everything mixed together, and it's incredibly, incredibly complex. And it's going to need all the science that we can bring to it. My premise is we come to recognize three phases of reality, and therefore causality, three kinds of reality in the world. The first and obvious one is ontic reality, physical reality, the concrete reality that science studies mainly reductively and not so holistically, because that is difficult. But that physical reality gives rise to a relational reality. We're part of that reality right now. My image and you hearing me is part of this relational reality. It has it has a physical basis, but it's not physical. It's not observable. It is relational and virtual. So these two phases of reality, physical concrete reality and aphysical virtual reality, are both objective. That is, they both exist without the need for some observer to ratify that existence. That is the third class of reality, which I've come to call cognic or cognitive reality, which is the reality that is individualistic in every species. That is, every species, no matter how great or small, microbial, macroorganisms, and so forth, have some cognition of the world that they live in. And that cognition registers as the nature of that world. And in our field, we call that a model. All living things make models of their reality, so to simplify their reality and make them and make things livable. So that cognitive reality, it throws a different complexity, because the organisms were changing the other two kinds of reality, the physical and aphysical, and those changes are coming from the organisms' conceptions, their cognition, their how they relate to the world. All right. So all three of these phases of reality are mutually implicated. They're intertwined, and they cannot be easily separated, especially the objective virtual reality and the subjective one, the third one, that is cognitive, that does depend on observer. All right. So there are 8.7 million species in the world by current count, which means there are 8.7 cognitive models, cognitive realities operating in those species to change the real world and the virtual objective world. So it's a very complicated set of circumstances. So we look at that as the three phases of reality, causality, and we come to a conclusion that causality is carried by complex networks, and these networks come from both above and below. That is, the lower levels of organization, higher levels of organization, and the entity, you and I as entities, in between. And the two poles must meet. They meet in the middle in a consistent object, and that is us. All right. So the talk that you're going to hear is concerned with some of the elementary characteristics of the networks that are carrying this causality, this bipolar causality in the three phases of reality, if I can put it that way. So with that, I'm very pleased to be here. I'm thanking Professor Banerjee and Professor Ray for the introduction, and I'm very happy to be part of this. So someday maybe I will meet you all, and let us hope that we're all healthy and that day comes sooner rather than later, because I'm getting old. Thank you all.
We are facing some technical issues at this moment. So we'll sort it soon, so please wait. We are really sorry. We are facing some technical issues. Everything was working fine during the trials, but our team is totally working sorting it out. We'll be, will hopefully be back on in a few minutes. So we request the audience to please bear with us.
Good day to you, ladies and gentlemen. This is Bernard Patton coming to you from the Odom School of Ecology at the University of Georgia in Georgia, USA. I'm going to talk to you about this title, The Wealth. Good day to you, ladies and gentlemen. This is Bernard Patton coming to you from the Odom School of Ecology at the University of Georgia in Georgia, USA. I'm going to talk to you about this title, The Wealth of Ecosystems. And by the time I'm finished, you'll know something about what I mean by that, where the name comes from. How autonomy, biodiversity, and connectivity, those three things, come together to optimize fitness in the biosphere. Biodiversity, this being a conference on biodiversity, will be, in a sense, the focal point. This date is 50 years ago in 2 weeks from now, and it happens to be the date when I started work at the University of Georgia. April Fool's Day, we call it. I came from Oak Ridge National Laboratory, ORNL. And the title of my recruitment lecture was The Network Variable in Ecology. And that had origins in my experiences at Oak Ridge, where we were doing radioecology, releasing radionuclides into the environment and tracing them and quantifying them. And I had a colleague, Martin Whitcamp, who was a
great experimentalist. And he was particularly strong in constructing, I say mesocosm, but they were medium-sized containers. He would put together 10 or 12 compartments, for example, forest compartments, some plants, some mosses, some ferns, some herbs, and insects, and a few vertebrates, soil, litter, and so forth. And there was a baseline configuration for these microcosms, and he would replicate them, 50 or 100, put them in controlled chambers, and rain on radiostrontium, radiocesium at the beginning of an experimental run, and then subsequently sacrifice subsets of these containers and determine where the radioactivity was in the compartments. Then I would make models of the experimental ecosystem, they were micro-ecosystems actually, and quantify the rates of exchange. What we found was that what you had in the containers, if you modified what you had in the containers, you would change the rates of radioactive transfers in the system. The transfer processes were eating, excreting, and so forth. That is, they were physiological processes that were owned, so to say, by organisms, not by ecosystems. But if you change the network, and Whitcamp did it by baseline configuration, and then he would add a compartment that is different, or maybe two, or subtract one, subtract another. So they had the combinatorics of that kind of experiment. And the net and overarching result from that work was if you change the network, the rates of physiological processes change. And I took that away as a major statement about what is going on in nature. In one word, it's holism as well as mechanistic causation. And I came with the idea that causality in nature is not just coming from below mechanistically and reductively, the way science studies it, but is coming from above as well. And they have to meet in the middle, and they have to be consistent in the middle, don't they? Because we're in the middle. The entity is the manifestation of these dual causations coming from underneath and coming from above. That was the takeaway message. And of course, we're interested in big systems, ecosystems. How do they work? The title, The Wealth of Ecosystems. We want to know about whole systems, how things operate together. But we can't take whole ecosystems and put them in growth chambers the way Whitcamp did with microcosms, can we? In other words, the causations are too many, too distributed, and the systems are too big. We cannot replicate them. We can to a certain extent do controlled experimentation within systems. Don't get me wrong. We can do a lot of empirical work, but it's not quite the same as having an organism like a laboratory white mouse or a Drosophila that you can go over and over and over and over again with the same system and learn about it in detail. So we have a problem, a scientific problem of how to use the scientific method, how to bend it. It says here, to study empirically inaccessible system properties, which is typical of big systems that are bigger than we are. And the answer, my answer, is apply formal systems science as an underpinning to systems ecology, and that systems ecology focuses on, quote unquote, the network variable in ecology. Change the network, change the system. That was our mantra coming here to the University of Georgia, and I've done it ever since. And over the soon to be 50 years, myself and mainly my students and research associates, small in number, developed a pretty coherent theory that I like to think of as an environmental system theory. It is an environmental system theory. And it's a state-space theory in that it uses the formalism of L.A. Zada's state-space system theory. Input, state, output formalism. L.A. Zada was one of my early entries, not my earliest, but the one that I latched onto into formal system science. He died this summer in Berkeley. I think he was 93 years old. Our unit, our study is the environment. All the theory, theory of environment, NEA, network environment analysis. Let me pictorialize this concept for you. We start with a compartment. Whitcamp had 10 or 12. Have hundreds of thousands. Storage elements, storing energy and matter. A compartment is always part of a larger system. And let's say a typical model system or typical system has n compartments. And the compartments and the system are both open, so they both have environments. They're receiving and giving their surroundings. The essential setup. Receiving, here is input I, Z, I, and a notation, and I will have some notations here that you'll be following, particularly in the early part, and output Y, and I've got a little color coding going too, typically. Blue and out is red, typically, but there's variation. And the within system portion of the environment of each compartment I is the input environment, and the within system portion of the outgoing environment is output environment. So you notice I've labeled these EI prime for incoming, and it's blue, and EI for outgoing, and it's input and output environments. So there they are pictured. And why only the within system portions of the environment? It's because environment, it's because we make a model of the system. And the model contains the information so that we can actually describe the environments within the system. Outside the system boundary, there is no mathematical description. So you can only receive inputs and generate outputs. Output environments are generated by inputs, and they produce what I like to term, think about as empowering. Input empowers activity, and enfolding. Input enfolds the material into the larger system. And on the other hand, the input environment reference to outputs reflects embodiment as in Aetiodom's embodied energy, and also unfolding. So those ideas are going together in this presentation. NEA, Network Environment Analysis, is in effect a boundary referenced input-output partition methodology. So here's a three-compartment open system. 3 inputs, Z1, Z2, Z3, 3 outputs, Y1, Y2, Y3, inflows and outflows internal, in black, and the summation of either the inflows or the outflows at each node is called through flow. And through flow analysis is one of our two key analyses, and the other is storage analysis. And you see them pictorialized both. The storage is x1, x2, x3, form a storage vector. The through flows, capital T1, T2, T3, form a through flow vector. So those two elements are derivable, are computable from the differential equations. All the analysis begins with an ODE description of the system. In this case, there are three compartments, so it's a third order ordinary differential equation. And it's an in minus out equation, you can see it. And you can see the inputs in blue and the outputs in red. And the inflows and outflows are the other terms in the equations. The environment analysis itself is a partition analysis. So each input is generating a unique output environment. So Z1 generates the flows and the stocks shown in the first diagram. Z2 generates the flows and the stocks in the middle diagram, and Z3 in the right diagram. And if those were different quantities or different colors, and for example, if the Z1 were blue, everything in that picture would be blue. In other words, it derives from that input. And then the second one, if the input were green, everything in that diagram would be green, etc. So you get the idea. So those are output environs stemming from inputs, and reciprocally we have input environs which are computed going backward in time from the outputs, backward in time and also in the network, against the grain of the network. And you see then, you see that we have a partition concept and a partition analysis. Let me illustrate empowering and enfolding for you using a chain, like a food chain, for example. A simple chain, I think this one has five units in the sequence. So we start with a blue input. So the stocks are blue because that's the only source, and the outflows and the output and the outflow to the next compartment is blue. The next compartment receives green input, let's say, and so the stocks have green and blue elements in them. The outflows have blue and green elements in them. Go to the next one, we have an orange input. Stocks have those three elements in them. You can see the enfolding of these inputs into the system. It's all, if it were energy, it would all be energy. If it were phosphorus, it would all be phosphorus. But their origin, the history is different. Brown, you have a brown one. So you can see what's going on here. Red, you have a red one. A progressive complexification of things being mixed up in the system. You had breakfast this morning. The ingredients in your breakfast came from far places in India or near places in India or far places in the world or all of the above, and they are enfolded in you now, and so forth. So the diagrams are simplistic, yeah, but they help us to see and understand what is going on. On the other end, now we're going to back trace these flows and storages to their origins, back traced in time through the output, through the input environs, and you can see the progressive diminution, the unfolding, and the embodying that is going on in these diagrams. Okay, so first look is one way, empowering, enfolding, propagated forward in time and output environs generated by inputs, and then embodying, unfolding, traced backward in time in input environs reference to outputs. The two looks are important, and we're going to get to that aspect in a moment. Looking forward and looking backward are two different views of the system. The networks are not, in this case, it's the same network. It's a simple chain. But in general, a complex reticulated network, if you look through it in one direction, then turn around and look back in the other direction, it's not the same network. It has different everything about it. Pathway realities are much more complicated than simple chains like these, and that is an understatement. Here's a textbook model of an ecosystem, Antarctic ecosystem, just to show you a real life, quote unquote, real life, a pictorial depiction of environs. In this is a textbook diagram. So let me come back. So we picked a focal compartment, the crab-eater seal, and we look back through the input environ first to the food of that animal, krill. We look at 2 steps back to the 2 food sources, one plant, phytoplankton, the other zooplankton, to the krill, and then finally 3 steps back to the food of the zooplankton. That's as far as you can go on this diagram, 1, 2, 3 steps back, because that's the way the diagram was constructed. We can also go forward 1 step. So the crab-eater seal is consumed by leopard seals and is consumed by orca whales. Orca whales also use seals and in addition are fed upon or are utilized, I said it would be a better way to put it, by man. And we can only in this diagram go 3 steps forward. But there you have the entity and its 2 environs, backward and forward, depicted, and the same is true for each and every compartment in that system. And NEA, network environment analysis, computes these relationships for all the compartments in a system simultaneously. Right? So we can reconstruct environments of entities in compartment models. It's a mathematical process. So let me just quickly give you a mathematical overview and some notations. Here's our 3 compartment diagram again. If we take those flows, the F's in the interconnecting flows, and replace them with 1s, then you get, and put them in matrix format, from columns to rows. I'll show you a number of matrices in this presentation, and they will always be oriented from the columns to the rows. All right, so A0 is the adjacency matrix with zeros on the diagonal. That's appropriate for a system that doesn't have any stocks, for example, any standing stocks. A1 has 1s on the diagonal, indicating storage at those nodes. Then the flows that go with those, notated in the diagram, so you see the isomorphism between the adjacency matrices and the 2 flow matrices that are used, one for storage analysis, one for through flow analysis. And then you see those vectors, input, output vector, state vector, and a vector of 1s used for computations and so on. Here, the flow equations on the left, input driven, the typical flow equation. This is for the general linear compartmental system. On the right, the solution effectively is going backward in time. When you do it, it goes forward in time, but the understanding is you're tracing back from output through the system, and you can see that the flow matrix is transposed in that case. So giving you a transposed network to pass through rather than the untransposed one in the forward direction. On the left here, then, you see through flow analysis, and in parallel with it, storage analysis. Those are the 2 key analyses of NEA, network environment analysis. And I'm just now circling the matrices that are going to figure in subsequent developments here. B, the mapping matrix for, you can see that B and B prime for the reverse case, and C, and later C is going to be replaced by C is not non-dimensional. To non-dimensionalize it, we convert it to P, and you can see over there on the right-hand side, right here, I'm circling it with the cursor. P is equal to I plus C delta T. So we convert C to a non-dimensional probability matrix, and that's the one that's going to figure in a little bit later in an example. All right, let me move on. I have a feeling that I'm going a little more slowly than I should be. The ABCDs of network environment analysis. Okay, this is going to illustrate the core analyses here. And there are the equations again, the first one for through flow, the second one for storage analyses, steady state forms of those equations, which are mapping inputs into through flows in the upper one block, and mapping inputs and outputs into storages in the lower block. State transition equations again. Now, from those, we derive pathway analysis by replacing the flow matrix with adjacency matrices and then taking powers of the adjacency matrices, generating an infinite series. In this case, the adjacency matrices are zeros and ones. You take powers of them, and they are infinitely divergent. So this is a divergent series. Through flow analysis utilizes the B matrix, and you can see that is taken to powers as well. And in this case, converges to minus B inverse, minus B prime inverse, which are the matrices up at the top that map the boundary relationships into the interior, in this case, through flows. Storage analysis, the same, another infinite series, mapping into the standing stocks in the system, and utility analysis, which takes both the B and the B prime matrices and combines them, and then takes powers of these. The D matrix is called a direct utility matrix. The U matrix on the right side, with the convergent matrix from that power series, that U matrix is a measure of integral utility. Utility is a value measure of the flows and stocks. How valuable are these in the system, in the network? And we think of that valuation in terms of benefits and costs to the processes that I'm going to describe, the optimization to fitness, to maximal fitness that I'm going to be describing for you. All right. So here are the B matrices as sums of power series, convergent sums of power series, and the C matrices as convergent sums of power series. In those power series, the first term is always the identity matrix, and that brings the input or output into the system, from which point it is progressively propagated forward or backward. The next term, the second term, is the direct linkages, the direct influences in the system, and all the remaining terms are the indirect influences. Now study that hard, or at least think about it, because those terms are defining a network of smaller flows, that is true, but a network that is very large, that becomes a very large numbered network with infinitesimally small flows, but so many of them that they add up to a lot. And we come to the point that the indirectness always dominates directness in a well-constituted, in a substantial system. Indirect effects are dominant in nature, is what I'm trying to say. You can see in these power series the implementation of the empowering and folding ideas, and also in the reverse one the same. All right, so you can see then the consistency of the methodology with the conceptual structuring. Here's an example from John Teal, 1962, one of the early classical energy flow storage models in ecology. This is from Sapelo Island, an island, one of the coastal Georgia islands in in my state. The flows in this system are energy flows and the storages. The flows are in kilocalories per square meter per year. And here is a digraph representation of that original diagram in Thiel's paper. And this was generated by an online software package developed by one of our colleagues at the University of Georgia, Janus Kazanyi. And it's a software that I can recommend to you. So if you get this link, you can open that link and it gives you an entry into NEA, Network Environment Analysis, and more. And it's illustrated right from the beginning. So you don't need anything going in. It's almost like a tutorial. It's been used in some hundreds of countries in the last decade or more. Thiel model. Okay, now we come to, I want to give you a sense of pathways and how pathways are working. Take the mind back quickly to radioecology, just to make that connection. We introduce a tracer. Where does it go? All right. So first, I want to identify some terminology. A simple path. A simple path is a path from one compartment to another over a chain like we had before, but there are no repeating links. There are no repetitions along the way. That is a simple path. And in the Thiel model, there are 29 simple paths in E1, the first output environment. That is the output environment that is generated by Spartina, the dominant grass, estuarine grass in this system. Here are the first 8 of those 29 flows. The diagrams are all the same, but these aren't. So I'm identifying the particular paths, and you can see them. Each point as you're looking at these is that each simple path in the system is unique. And that's that. Each one is unique. So there are many ways to pass through a system. The remaining 5 of those 29 coming from Spartina are these. Those simple paths touch in these models by virtue of shared nodes and flows. They touch cycles. And in this model, there are 5 simple cycles. A simple cycle being one that starts at a compartment K and comes back to K. That's a simple cycle. Of course, it goes around again, so they're 2 times around, 3 times around. So cycles, by definition, are infinite in length. But a simple cycle is the first time around. So there are 5 simple cycles in this model, and here they are identified. The first 2 are 2 cycles, 2 links in those cycles. Those 2 cycles have a property we'll talk about later, symmetry, and it's an important property. It's a significant property. You'll see how it figures importantly in cycling in systems. The next 2 cycles are 3 cycles, 3 links. And the last cycle there has I believe 4 links in it. All right. So again, each simple cycle is a unique entity in the network of that system. Then there's another source. The algae compartment also receives input in the Thiel model from outside the system, and there are these simple paths in the second environment in E2. Okay, so those are simple paths. Now let's talk about compounding. The pathways compound when simple paths touch simple cycles. Then you have cycling introduced into the entire pathway structure. The third element, you'll notice the terminology walks identified there. Our terminology is, a walk is a path that contains self-sequences along it. For example, we start at J, we end at I, but we come through to K, and then it reads K to K to K to K to K to K to K. So it's staying where it is, but then it goes on to L or M and so on. That staying where it is part is storage. And it is also time passage. So time is passing as the material is moving through the network. Here are the first five powers of the adjacency matrix for the teal model, the Sapelo Island model. In the upper row, first five, and I'm going to focus on the 3-1 node in each case here. There's the diagram, the diagraph from EcoNet. You'll see that there's one link, one way to get from compartment 1 to number 3. In A squared, there are 4 walks from compartment 1 to compartment 3. In A cubed, there are 13 ways to get material from compartment 1 to compartment 3 in 3 steps. In the fourth matrix, there are 39 ways to go in 4 steps from 1 to 3. In the fifth matrix, there are 113 ways, and so on and so forth. So you can see where we're going here. We're exponentiating. As pathway lengths increase, the numbers of pathways increase exponentially. What does that mean? It means by the time you get to a number like A to the 100, a path of length 100, you have 10 to the 45 pathways to consider. 10 to 45 is a huge number. I'll show you how huge in a moment. Our minds don't really go there. All right, so do these long pathways transfer any significant substance? What's your answer? I can't hear you. Would I be standing here if the answer were no? No, the answer is yes, indeed. They transfer significant substance. So that's the reticulation. The network variable is born on this idea of many, many pathways reticulated in the system. So let's do some flow accounting and see just how much is contributed by various components. The direct flows in the teal model come up to 84, 85, call it storage units, calories per square meter, 85. The total flows in that system account for 1,228 calories, all right? Of that 1,228, 85 are direct. The remainder, 44 rather, are indirect. And going back here to a pass, not of length 100, but all paths up to length 100. All right, so at path length 100, we know there are 10 to the 45 walks. At path length 99, one step sooner, there's something less than 10 to the 45. 98, something less, and so forth and so on, all the way back down to the beginning. Huge numbers of pathways are carrying 1,176 calories per square meter in this system. How much is that? And remember that A to the 100 is 10 to the 45. 96% of the flow is accounted for through pathways up to length 100. 5%, 4.3% remains to be accounted for in pathways of length greater than 100. There are 10 to the 22 stars in the universe, so the astronomers tell us, and there are 10 to the 81 elementary particles in the universe. So in the universe that is the Teal salt marsh model, 1962, going up to pathways of length 100, there are 10 to the 45 such pathways. That's context. My title. Where am I going with that title? Wealth of Ecosystems. It comes from a book, important book, Wealth of Nations. You all know it, I'm guessing. By Adam Smith, 1776, 270 some odd years ago. Wrote this sentence on page 552 of a 1,300-page book. Every individual intends only his own gain. Everybody was masculine in those days, we know that. It's changing now. And he is in this, led by an invisible hand, to promote an end which was no part of his intention. That sentence is so profound in terms of the ecology that I'm about to present to you, that it's amazing that this man had it almost 300 years ago. The invisible hand concept, of course, is now famous in economics, and over the almost 3 centuries since Adam Smith, it has not been mathematized. And I can tell you that we think we are close to mathematizing it, coming from ecology. Not there yet, but we have the general idea, and I'll be able to make that clear to you before this is over. The 3 elements in Adam Smith's set of ideas were self-interested people. Self-interest was core. Division of labor. The first chapter in his book is about division of labor. So the most important thing was right up front, division of labor and free markets. That's the economics. He, in the course of that description, discussed division of labor. And he used a pin factory as an example, where pins are made. And he contrasted the making of pins by method A versus method B. Method A was you and me and somebody else are workers in the factory, and we take the raw materials to make the heads, to make the pins, the wires, and everything that is required to sharpen them, to make them symmetric, to attach the, and one person does all of that, versus all those jobs, 5, 6, 7, or 10, or 13, however many there are, is a specialization, and one person does only that. And then at the end, those specialized products, the output from those specialized endeavors, are put together and assembled by another group of people who know that job. Division of labor. And Adam Smith said, that the and showed the output. You can do this as an experiment. The output is enormously greater when you have such division of labor. So, self-interest, what does it mean? Autonomous units. That's you, that's me, that's the organism out there in the ecosystem. Everything that lives is self-interested and is autonomous. Division of labor, what does that mean? Biodiversity, that's what this conference is about. How does biodiversity contribute to ecosystem development and free markets? The fact is the ecosystem out there is free for occupancy. It's not like it's a machine, and if a part breaks, you have to replace that part exactly in kind. That's not the way ecosystems work. They work as free markets. Whoever gets there and can stay there in the Darwinian struggle stays there. So you see immediately the parallel between the economy of nature and the economy of nations, Adam Smith's orientation. My subtitle then, autonomy, biodiversity, connectivity, how these come together to optimize fitness of the biosphere. And that brings me now to my very personally troubling hypothesis. I call it the Janus hypothesis. Everything so far has been 2 looks. Look one way from inputs, look the other way from outputs backward, and so on. Janus is the Roman god of beginnings, starting, and endings, ending, and in-betweens, the network that is connecting beginnings and ending. So the Janus concept fits this program that we are developing. 5 conjectures make up the Janus hypothesis. They are, first one is a premise, or an axiom even, you can call it. In NEA, aggregation, network aggregation, I haven't given you this term yet, but it's the movement away from thermodynamic equilibrium. So the maximum entropy condition is everything is randomized, there are no gradients, there's no movement, boom, it's dead. Maximum entropy. Degradation, energy degradation is the second law of thermodynamics. Aggregation is movement away from that circumstance. That's what life does. That's what living things do. They aggrade. So, network in NEA, our term for that movement away is aggregation, and it's quantified by intercompartmental flows, through flow, and storages, the standing stocks. Total system through flow, TST, total system storage will be measures that we'll be focused on. Premise 2. In NEA, through flow weighted network synergism signifies always positive net utility benefits greater than cost, and is quantified by the extent of this balance. Network synergism, networks work to generate global positives from local neutrals, plus minus interactions. I give you something, you receive it, that's plus for you, and I get an equally weighted minus. It's a consumptive interaction, like predation, like eating, and many other such exchanges. All right? Theorem. The third conjecture is a theorem. Maximize network aggregation is to maximize total system through flow and total system storage. Total system through flow is what we would call productivity. Economists call it productivity. Total system storage, we would call it product or capital. Potential. Kinetic is the flows. Storage is the potential. Departure from equilibrium. So there's theorem 1. And theorem 2 is the Janus theorem. You maximize total system through flow and total system storage. That maximizes network synergism, which is the dominance of positive, more positives than negatives at the end of the chains of causation. I'm going to show you this in just a moment. And then finally, maximum network synergism corresponds to maximum fitness 2, we call it, biological and environmental fitness. That is biospheric fitness. So, maximum total system through flow, we call goal 1, that's wealth. That's the wealth of ecosystems in the title. Storage, network synergism rather, is the preponderance of positive over negative relationships that reflects on the health of the system. And the third goal is fitness 2, and that takes it up to the biosphere level where the health of local ecosystems maps into in a general way, in a larger system way, the welfare, the ongoing well-being of the. So we have these 3 elements then: wealth, health, and well-being of this graded series of systems. Here's a picture of the Janus hypothesis. On the left, you see the network aggregation nexus: autonomy, biodiversity, connectivity comprise that nexus. And let me show you the remainder of the diagram. The upper part concerns adjacent transactions. These are immediate links, the passage of food between things, the passage of causality carried by energy and matter. Conservative, zero-sum, and win-lose relationships. And in the lower part of the diagram, we have the place where indirect effects dominate and give us ultimately the network synergism outcome. So let me just then talk my way through this diagram, beginning with the second law. The goal function, the goal of living systems is to stay away from the death state that the second law brings you to. So we're talking about anti-entropic activity. The aggregation nexus contains all the mechanisms, the living and non-living mechanisms that combine to produce this movement away from equilibrium. The outcome is to generate maximum through flow and storage. The adjacent effects and conventional empirical ecology are operating to produce Darwinian fitness, organismal fitness on the right. The outcome in these processes, the organisms are gaining, but they're taking resources, they're taking things from the environment. So the environment is getting closer to equilibrium, so it's being degraded in the process. In the lower part of the diagram, the opposite happens. Indirect effects, if you follow them locally, the upper part of the diagram applies, but collectively, the lower part of the diagram applies, and it becomes a shift to from adjacent plus-minus relationship to network synergism, which tend toward plus-plus relationships and the dominance of positives over negatives. System's entire system is enhanced in this process, and that's fitness 2. So goal 1, wealth; goal 2, health; and goal 3, well-being, are reflected in this Janus look at the hypothesis. Now let's take and by the way, the sequence then: autonomy, biodiversity, connectivity. Those 3 things maximize network aggregation, maximize wealth, that is through flow, whole system through flow and storage, maximize network synergism, health, and ultimately fitness, represents Adam Smith's economy of nature rescaled to the economy of nature. The Janus theorem now is what I want to call to your attention. In the original paper where I published, when I published the Janus theorem, the Janus hypothesis in 2016, I gave 3 lines of evidence. A simulation line, building a biosphere, I called it, and I'm going to show you the outcome of that here. Second was a symbolic MATLAB exercise that developed the information that network synergism, the goal of the Janus process, that network synergism contains through flows in complex algebraic relationships to one another. I won't show you that because it's too complicated to even begin to start. And third is the comparative ordering by through flow of 31 empirical food webs. And I will give you a sense of that. Let me go back to this. The theorem, the primal theorem that maximizing storage and through flow is sufficient to maximize network synergism on the right. In each of the blocks, the left side is sufficient for the right side. The right side is necessary for the left side. The two bars down the middle are equal signs. So the theorem and contrapositive are logical equivalents. The converse and inverse are logical equivalents. We do not have a proof of the Janus theorem. I've begun to doubt that there is a proof, because it would say that if we maximize the through flow and storage, that we would then automatically maximize the network synergism. And I think that's not the case. I think there's more work to be done to get to a maximum network synergism. But for the converse, there is a proof, and that has been given by one of our mathematical collaborators, Malcolm Adams, and he's writing the paper now. It's a short proof, but what it does, it shows that through flow, total system through flow is the upper bound for network synergism measured by through flow. And presumably total system storage will be the upper bound for it measured by storage and so forth. I haven't seen that, but I think that will follow. So the converse is true mathematically. That's a strong, strong result because it means the inverse is true. And what the inverse is environmentally troubling. Because it says, if we do not maximize the total system through flow, the productivity of the system, the product, the storage, if we do not maximize those things, you cannot maximize systemic network synergism. And if you cannot maximize systemic network synergism, evolution says somebody else will. So in other words, the system is evolving to generate this kind of result. Environmentalism, conservative conservation ethics and programs are trying to power down the use of energy, the use of matter, and so forth. And here we have a theorem proved that says to get the system up to the best that it can be, furthest away from equilibrium, you have to do this maximization process. As I said, it is troubling, including for me, because I'm an environmentalist too. But these are the facts. This is what the theory is saying. What it will mean next year with further clarification or something else comes along and so forth remains to be seen. Right now, this stands. It's a problem for me, so much so that when I published this paper, I called the theorem, the hypothesis, the Janus enigma hypothesis. And this is the enigma in the inverse. If you don't churn the system, you're not going to get the best benefit out of it. So that stands right where it is. Evidence, synthetic networks. We started with a single producer compartment. Put in 10 units of input. We see 10 units of output coming out. Total system through flow is 10. Network synergism, zilch, none. Sorry. There's no network synergism possible from that configuration. If we add a saprotrope that receives some of the dead material and can process that, then we increase both the total system through flow and we increase the network synergism. It jumps up from 0 to 10. If we add an herbivore to that prior configuration, we've increased the total system through flow, and in this case, the network synergism stays the same. Here, we'll now take the dead material, let's say from the herbivores, and put that into the saprovores. That bumps up the synergism to 10.18 over 10. Here, now we're extending the chain to carnivores. 10.41 is the synergism. Total system through flow increases. All these systems have only 10 units of input, but they're generating variable total system through flows and variable network synergisms. Right? So here's a 6-compartment system with more connectivity, some cycling. There's a 2-cycle between the mixotroph and the saprovore. And here's further connectivity. We're up to 10.99 network synergism. Here we're up to 11.93. More connectivity is happening. And here's the max in the sequence. So you can see how the 3 elements I described, autonomy, the very first compartment, can generate no utility, but it can generate some through flow. But as soon as you get some interactions, other things begin happening. All right. Synthetic networks, just summarizing, we took in that sequence of 10 examples, we went up to 6 compartments. And then, so that's why it's flat after that. And then we focused on the connectivity. Boundary input was the same, and outputs were the same. The number of links increased gradually. That's basically what the sequence was demonstrating. The total system through flow increased following the linkage, and the network synergism after the first one jumping up increased also following that. So there you go from that. That's it. So that demonstrates a synthetic network. Biodiversity, N, number of components, connectivity, number of links, through flow, wealth, network synergism, health, all trending upward. Food webs. This is the empirical evidence from our colleague Oksana Bustihan, who worked for her dissertation in Ukraine, describing 31 pastoral food webs. These were large food webs with many, many nodes and links. She mobilized an army of students, graduate students and undergraduate students, to do the collections at certain times of the year, bring them back to the laboratory and do the picking and sorting to generate the feeding relationship. So it was an enormous piece of empirical work to generate the data. Here's a tabular depiction, a listing of the compartments ordered by total system through flow, least at the top, most at the bottom. There were 41 to 135 compartments in the series, 147 to 977 links in the series. Total system through flow went from 109 to 426, and network synergism went from 219 to 702. So, biodiversity, N, connectivity, L, wealth, total system through flow, and health, network synergism, all trending upward. Must I calculate a correlation coefficient for you for these things? No, you can see that they're all strongly correlated. So, the ABCs then of the Janus conjecture, let's retravel that ground by way of leading up to my showing you how this happens. Aggregation nexus, the three elements in my title: autonomy, biodiversity, connectivity. Total system through flow, we want to maximize that. Network synergism, we want to maximize that. And finally, fitness, we want to maximize those two measures of fitness. How does this work? That's the question we are concerned with, because the idea is that collectively they comprise this invisible hand of Adam Smith's, only now in the ecosystem. So how does it work? So the screen is okay. I did that for a reason, to show you some surprise elements in this process. So now, let's sort of take a breath and start at the beginning with some new definitions, a new track. It's the final track, not too much longer in this talk remaining. Ecological networks are transactional interconnections of living and non-living components. A transaction in ecology is an energy matter flow. It is conservative. It is zero sum between two binary elements. In economy, in economics, it is money flow. All right? And GDP in economics corresponds to TST, total system through flow, in our usage here. An energy matter transaction is a binary relation, ATB, defined by a conservative zero-sum interchange between two adjacent substance storage compartments. So you see the two compartments, and A is in the relation T, transacts. A transacts B. Transactions are the base relations in physical networks from which other kinds are constructed. So let T now be our relation aggrades. Aggrades meaning moves the system away from thermodynamic equilibrium, such that ATB I just said it, moves the system away toward order, away from entropic disorder, away from the heat death, so to say. Binary relation, the defining properties of binary relation are, this is repetitive, everybody You all know this material, this being India and everybody here being well educated and it being a mathematical conference to some extent. So, forgive me, but a binary relation then between two sets A and B is a subset of the ordered Cartesian product set A cross B. Statements A are B. Those statements, the way I've written them, they all mean the same thing. A is in the relation R to B. And I'm going to make that clear with a few simple examples, like kinds of textbook examples. R is reflexive if A are A for all A in A. Example, equals is the canonical reflexive relationship. A equals A, all right? T aggrades is reflexive for living systems. A aggrades itself. There's your self-interest property immediately. R is transitive if for all A, B, and C, A R B and B R C implies A R C. Example, the relation eats is intransitive. If A eats B and B eats C, that doesn't mean that A eats C, does it? So that's not transitive. But aggrades is transitive. If A aggrades B and B aggrades C, then A aggrades C. And it's this transitivity of aggregation that is a key property in what we're developing here. Finally, R is symmetric if both A are B and B are A. So, for example, in the human domain, loves is conditionally symmetric. John may love Mary, but Mary may or may not love John. I mean, she does, then it's symmetric, okay? But mates with is a symmetric relationship. If John and Mary mate, they both are involved, okay? It takes two to tango, as it often is said. It grades may or may not be symmetric. Okay. Synergism. Synergism is the interaction of discrete agencies to produce emergent properties, emergent total effects greater than the sum of individual effects. The synergism hypothesis, Peter Corning wrote a book, 1983. Co-determined, interdependent, cooperative phenomena create evolutionary complexity in natural and human assemblages. Half of his book is concerned with ecology, the other half is concerned with sociology and human system. Network synergism is our property that we've been talking about, but quantitative emergence of system-wide positive greater than negative utilities in energy matter flow storage networks whose maximization is necessary to achieve maximum biotic and environmental fitness. Okay, that's the Janus hypothesis. Synergetics rather, and toposynergetics, all right? New ideas here. Synergetics is a term that Buckminster Fuller coined to express structural transformations of systems not predictable from properties of components of those systems. Herman Hockin wrote a book called Synergetics some years later, and he elaborated this phenomenon from the perspective of laser theory. The word laser is, in fact, an acronym meaning what it says there, light amplification by stimulated emission of radiation. Toposynergetics, not an awful word, that's my word. Okay, I don't know how to get around it, but it means the topology of the system, the connectivity is responsible for this synergetic kind of response. So in transactional networks, compartments not interacting with others, only with the external environment can reflexively generate the network synergism basis of biotic environmental fitness. So for example, plants can live by themselves in the greenhouse, or they could live out in nature and never have any interactions. All you need is photons and some mineral and some nutrient elements and so on. But that's not the way plants live in nature. They live like everything else lives, interconnected with other things. Intercompartmental transactions themselves possess little such capacity to generate storages and flows. But when transitive and symmetric properties are combined, then this process of tsunami happens. And that's an acronym also. Through flow and storage, utility network amplification by maximizing interactivity. It happens, and I'm going to demonstrate that, at least one example of it. So it's toposynergetics because it's the node link topology that produces this laser-like amplification effect. I'm going to demonstrate that by contrasting three separate compartmental systems. The first is an oyster energy model that we've used over and over again in NEA developments through the years. The second, the Sapelo Island energy model that I've already discussed with you a little bit. The third one, Neuse River nitrogen flow model, where nitrogen is the numeraire, the currency. You can see that these systems are variously connected, and in the case of the first two, they have a fin cycling index of about 10%. The third one is about 90% fin cycling. Okay, and that amount of cycling is due to the very great presence of symmetric relations in the system. All right, so these are the reflexive elements. They are the nodes. Self-interest. They are reflexive. They are self-interested. These are the transitive, but going away transitive. That is going away from origin. Where the origin? It's at the top, where in the first two diagrams, energy enters at the top and then moves through the system. So that in a downward direction in this diagram. In the right-hand one, energy comes in at the top of several compartments, but in general is moving away from those sources. We call that leaving transitive or L-transitive property or asymmetric. Then we have another form of transitivity, which is returning transitivity. You can see that these arrows are pointing back to origins where they came from. They're all oriented upward in those diagrams. So we have leaving transitive and returning transitive. And then finally, symmetric, we have 11, the cycling indexes show the symmetry, and the symmetric relations are these two cycles. There's one there, here, a two cycle here, here and here. There's another one over there. Here's one, here's another, and over here there are, I think, 5. 1, 2. You can see them sort of side by side. Those are the symmetric relations in these systems. Giving those digraphs a probability matrix representation, now we want to take that P matrix, the P storage mapping matrix, and partition it into reflexive components, L-transitive and R-transitive components. That's what we're doing here. So here's the oyster model, P matrix. Here's the P matrix for the salt marsh model and for the nitrogen, Neuse River nitrogen model. The reflexive elements are the diagonal elements. You can see that the probabilities along the diagonals are high in every case. The diagonals are representing this reflexive property, this self-interested property. I've got energy, or I've got the nitrogen. I'm not letting it go. I'm holding on to it. It's valuable. I've gone away from thermodynamic equilibrium. I'm going to stay there. That's what the high probabilities are saying. The L-transitive portions are the blue triangles, the lower triangles in this orientation, again from columns to rows, and the R-transitive portion is the upper triangle. So we had two forms of transitivity, going away and returning transitivity. And then finally we have symmetry, and symmetry is always pairs. I showed you the pairs in the diagram, and here there's only one pair in that model. There are 2, and over here there are 5 symmetric relations. So this shows how these relational components relate to the matrix representations of the system. Now, network amplification with total system standing stocks, Oyster, Sapelo, Neuse River Estuary. Here are the black numbers, the total system storage, total for the system. You can see 3,000, 1,200, 5,700, and that contributed by reflexivity alone, that is the self-interested part. In the first case, 2,000, 550, and 150, amplification factors of 1.53, 2.21, and tsunami 37.76. Those amplification factors are telling the story. The transitive components, the transitive parts of the lower triangle and the upper triangle contribute very little. They have to be coupled to the self-interested components along the diagonal. And once they are coupled, then you get various amplifications. And again, the main one of interest here is the Neuse River Estuary, which, because of the high cycling index and the high number of symmetric elements in that system, typically you get this enormous amplification. Well, we're expecting that this will become a phenomenon that will be generalized as we begin to learn more and explore these relationships. These are new things for us, even. We've been at it since 1968. Yes. Conclusion: the wealth of nature and nations both is generated by the same principles. Adam Smith laid these down for economics 270 some odd years ago. They're enunciated for ecology in the Janus hypothesis. ABCs: self-interest, division of labor, giving and getting, L&R transitivity, give network aggregation. Interestingly, L&R transitivity corresponds in human affairs to left and right persuasions. That is to say, left being progressive liberal and right being conservative, regressive, and so forth. That again is an interesting correspondence, that all elements are necessary. We need both conservative approaches and liberal approaches or progressive approaches to maximize this. Nature knows that, and by its free market activity, mad scramble to the struggle for existence, Darwin comes out with the greatest good for the greatest many, as Adam Smith refers to it. Tsunami amplification requires all three aggregation generating forces: reflexive, transitive, and symmetric. Self-interest, giving, and getting are all required to maximize the wealth, health, and well-being of systems in the economy of nature and nations. The Janus conjecture, this sequence, a maximization sequence, network aggregation, implies productivity and product, implies network synergism, implies systemic fitness, collectively is the invisible hand. Only, I would say, there are now two of them left, a left hand reflected in L transitivity and a right hand reflected in R transitivity. Thank you, ladies and gentlemen. It has been a pleasure to be here. I hope you find this material new and different and interesting, something to be further explored and further developed, I'm sure.
Thank you so much, Professor Patton. That was a wonderful lecture. Again, we would like to briefly apologize for the technical glitch that happened earlier, but I really hope everyone enjoyed the lecture. Professor Patton, we have a question from Prabhat Kumar Swain. He wants to know that the ecosystem of the present world is more damaged due to the increased demand of the human development and civilization. How to optimize and keep fitness of the biosphere in this present world?
Yeah, it's a good question. They seem to be conflicting, don't they? The theory, the present theory, the network synergism theory is basically verifying what we see in nature. Everything grows in nature. And in human economics, the growth imperative is a controversial imperative. Not in economics. It's important in economics that growth continue. Economies have to grow to be viable. This is reflected in ecosystem as well. Everything grows all the time. So knowing those obvious facts, the movement, the environmental movement wants to slow growth. And what I have to say then, from what I know now, if you slow the growth, you're going to slow the movement away from thermodynamic equilibrium, which is organization, which is biological organization, biospheric organization. So that nature is proceeding on a maximizing growth imperative, but we know that nature doesn't care who wins in the game, in the evolutionary game. So we don't say this, but we're coming at it from our point of view, humanity's point of view. We are a species, and all species are reflexively self-interested and trying to stay alive and continue. So that is the conflict. So where am I? I really don't know. I don't have a definitive answer. I think what we do know, let me put it another way. We have to get the science right in the first place. We have to find the science and then secondarily find ways to live around that science. If we go against the science, and right now, from my understanding, the growth imperative is going against the science. So if we choose not to grow because we want the values that drive that, if we choose to go that route, it means that we're coming off, we're moving away from the established objective function of evolutionary nature through billions of years, millions and billions of years. And if we do that, then I guess my claim might be other things will come in to find ways to maximize that growth. And therefore, we will slowly disappear. Of course, the timescales don't concern us individually because they are, thousands and years and several millions of years before these processes play out. So myself, personally, I am living now in this time, and I want a nice nature. I don't want pollution. I want to be healthy. I want to be vigorous, and I want all the organisms around me to have the same. So it's a fundamental conflict, and I do not have a resolution. I'm sorry. So, Dr. Swain, that's my answer. If you have an answer, please inform me, because they're definitely in conflict, aren't they? This theory is in conflict with the ecological growth, with the ecological imperative to slow growth and for example, climate change, global warming. Right now, this is this is the Holocene, but this is a period in the Holocene. And it may end up to be a 5,000 year period, or a 1,000 year, or maybe longer. But we saw this in the ice ages. Each of the ice ages, 4 or 5 of them, within each one had excursions. So just exactly like this, climate changing, small excursions, small in the big picture of thousands of years. But of course, at the time, they were major interludes in this process of glacial, interglacial occupancy during the Pleistocene and so forth. So my final answer is, let's get the science. If we're scientists, let's get the science right without regard for management, politics, and so forth. Let's get the science right and then build our systems around the science. We all want a good nature and everything to be alive and well and healthy. Okay. Thank you.
Indeed, sir. Thank you, sir. We have another question from our convener. Ma'am, if you're there.
Yes. I wanted to ask Barney, and it is such an enriching talk we just heard from you. So thank you for that. I wanted to ask you about the C-script or the cryptocurrency, that a concept that you have been working on, especially in context with the present situation, where the world is seeing an unprecedented, slowdown in just about everything. If you would like to talk about that.
Do you want to try to explain it, or do you want me to try to explain it?
Yes.
Maybe.
Yes. Try and explain it, and then maybe we can have some more discussion on it and around it.
What Professor Banerjee is referring to is something new in my life. My whole life has been new, as many of yours, in the sense that I've lived alone since last March, the middle of March. And living alone with only contact basically with one person who brings my food. Most of the rest is, it's because of my age that I decided I was at high risk and I was going to maintain a rigorous quarantine. But early in that period, I had some email exchanges with many of you. If you're ecologists, you know H.T. Odom, Howard T. Odom, very famous systems ecologist, one of my lifetime heroes. And I had some email exchanges with his daughter, Mary, just at the end of March and the beginning of April last. And in the middle of those discussions, the economy was beginning, the American economy, but also economies around the world were beginning to become unstable. And one could visualize that there were economic problems ahead as the pandemic proceeded. And meanwhile, I had from two sources, really. One, the New York Times, which I take and read, had articles about cryptocurrency. And at that point, when I first hit that word, I didn't know what it was. I had to go to Wikipedia and find out about cryptocurrency. But then the person who brings my food, who I mentioned, came one day and mentioned Bitcoin, and then it rang the cryptocurrency bell. And then my wheels started turning, and I thought, you know, we are a species. Technology is going to be with the whole future of mankind. We are deviating from any other species that we can sense is there in nature in having this kind of quality, where we are creating a kind of, well, just call it technology. We know the ramifications. We're here now because of it, this moment. And that technology is going to be with us. And I thought, why should we let the population crash? The economy crash. Why have people go hungry? Why have people lose their jobs? Why have businesses go bankrupt and out of business? And all those things are happening. why not stop that using technology? And the technology that I erected, and I can tell you, I've never had a course in economics. I don't know anything about information technology, and certainly not about money and finance. But those are the areas that we are working in. So I started coming at it from an ecological point of view. What do ecological systems do in times of stress? And basically, they don't try to keep going under stress. They try to change, and they change very quickly to meet those stresses. And I use some examples. There's the title of the paper. There's there is the ecological example. You have a normal. Well, okay, if the picture stays up, let me not wander. Let me just stay on the track here. The idea that I came up with is, why not, when a unit, a geographic unit or an economic unit, political unit, like a country, when it knows it's going to have a problem like this, close the economy, freeze the economy, declare an emergency, and freeze the economy right there in that moment in one day. So the economy is frozen. What does that mean? It means that all the assets and liabilities of all the economic entities, individual people, businesses, organizations, and everything is frozen. And if that were not the case, nighttime would come and the next day you would wake up and the economy would resume. But if you freeze the economy and fast forward to some other future point in time, then all you've done is change the next day there to the next day. It becomes that day when the emergency is undeclared. And meanwhile, to keep the economy going, you use cryptocurrency. And I named it and made a program. The next slide shows the protocol. I called it, I named the cryptocurrency cyberscript, basically. And if someone is in control of the slides, the next slide would be welcome, because I can actually use it to that slide. Hold that, that's good. So at the top, you see a building which is part of our Federal Reserve banking system. So the idea is then you have the dollar economy on the left part of that slide is on what's called DE Day, the Declaration of Emergency Day. That dollar economy is frozen, and you can see on the other end of the slide, the dollar economy resumes after the emergency is lifted, EE Day, emergency expires. And in between, you've established accounts, cryptocurrency accounts for individuals and households, for two categories, businesses and industries, institutions and governments. And the Federal Reserve is making disbursements to the white arrows, number 6, is making periodic disbursements of phantom currency. It's cryptocurrency. It doesn't cost anything. It doesn't exist. It's virtual. So it's absolutely free. And the whole economy then runs during this emergency period on that cryptocurrency. People have enough money to meet their basic needs. They have food, they have healthcare, and so on. All the obligations are canceled. They don't have to pay rent. You don't have to pay for obligations. You're not going to be unable to pay rent and be ejected from your home, and so forth. None of those things will happen because the economy has kept going with cryptocurrency, right? But then I decided that rather than, and then if you came to the end, the economy would still be viable. Everything would be as it was at the beginning. back into the dollar economy, and it wouldn't have costed anything, only cryptocurrency. But then you have incentives. What's the incentive for people to work if they're not going to make something out of it and so forth? What's the incentive for businesses to try to keep going? Well, the big incentive is not to be hungry and not to have to close your business because it's failed. So those things happen. But I decided I would go to a phase 2 and think about, okay, background for this is at the time it was becoming clear the social, because of Trump, because of our president, who amplified the things wrong with our country, deep problems that handed from the past that have never been resolved, racial problems, but all those things then were then at the beginning of the emergency and now continue to be discussed. And with elevated sensitivity, we now know about these problems. And so I tried to think of ways to use cryptocurrency to go to the next phase after the emergency to solve those problems. And the way to do that was to make the cryptocurrency that enters the system from the Federal Reserve to have an electronic tag so that it is permanently tagged to the receiver of that particular unit of cryptocurrency. And that particular unit of cryptocurrency can only be spent one time and only by the original owner of it, the original receiver of it from the Federal Reserve. The result of that means that all of the accounts that are established, of the millions of accounts that are established of various kinds, accumulate cryptocurrency because they become a sink, because you can't spend it. Only the original owner can spend it, and then only one time. So after the emergency, you have this huge pool of nothing, but it's not nothing. It's cryptocurrency. And it's a record of the gross domestic product, or in the ecological terminology, the total system through flow. It's a record of that because each transaction, one-time transaction, becomes registered in the storage, and that then is a measure of the gross domestic production during that period. The point is then, why not redeem that stored cryptocurrency? That's the idea. So, and then the scheme that emerged was, we redeem it such that the rich people who already have plenty don't need very much. So we'll take their share and we will redeem it to the lower people to raise up I wish I had the curve of the percentile distribution of wealth. The percentile distribution of wealth in the USA and in many other countries, but especially the USA because of its reflexive capitalism, greed-driven capitalism, it's an exponential curve rising from the first percentile to the 100th percentile. It's an exponential curve, all right? But it doesn't rise smoothly like I've just drawn it. It's flat. It's flat, flat, flat. Almost nothing until you get to the 90th percentile. And then it's flat, but going upward, exponentiating. In other words, this is, if you know our politics, you know Bernie Sanders, and he always talks, one of the failed candidates, he always talks about the 1%. He's talking about the 1% of the hyper wealthy people in the country, okay, who are reflected in that curve. So the idea is to use that curve and redeem cryptocurrency to dollars proportional to where you personally are on that curve of wealth. And there are all sorts of algorithms, ways to do this, okay? But that gives you the idea, okay? That gives you the idea. So, and by rebuilding by elevating people economically, you are going to make it possible for them to join the society more productively. Okay, so you're changing the flavor of society. You're lowering that 1% and you're raising the vast majority of the population economically. And as soon as that begins to happen, the social problems begin to go away. Let me give you one example. We have the highest prison population in the world because of all the injustice. And we could begin a prisoner conservation and reconstruction corps, a uniformed group organization that takes prisoners and teaches them how to do things and puts them out in the society to do the things and pays them to do that. And they take pride in membership. They wear uniforms. They're part of a corps. They're respected members of society. And the whole, I think you get the idea. If you meet the needs of people, the social problems begin to go away. So that's the idea. And it goes on and on into a third category.
I think it's a very intriguing thought. I think it's a very intriguing thought, and especially, Payal, if you go to the previous slide where Dr. Patton explains very nicely how nature does it. And what you just talked about, Barney, if it was fair and only the system drove the directionality of wealth, I think it would work very well. But I think in economics, in politics, one has to also factor in these other unforeseen forces. So people with vested interest and the all the gamut of things, which I'm sure nature also has to contend with in terms of stress. But then we can only hope that the system will autocorrect and we will be back. Soon the new normal will be over and we will be back on track. So with that, Professor Patton, I think you need to unmute yourself. Yeah. So with that, I would like to invite Professor Shantanu Rai. Is he there? And we can stop slide sharing. Thank you. So Shantanuda, if you could, sum up Barney's wonderful talk.
Thank you, Ina. And first of all, I congratulate Professor Patton. Thank you for your extraordinary talk, and we enjoyed a lot. One thing I can say like that, so far his career is concerned, you told all that he is actually brought up as a geologist, but whatever the matrix he is handling now, and matrix is one of the toughest, so far the mathematics is concerned, he can move anywhere in the matrix, and whatever the knowledge he has in matrix is really amazing. And most of the people here are from biological background, maybe some are from other background, and Professor Patton is from biological background, but how much he has the power in mathematics and what type of things he is doing with the help of the matrix. And one thing I'm telling you, the autonomy, biodiversity, and connectivity. So these are all the properties of the ecosystem, biosphere. And so the autonomy, and if you think all in a single platform, these are very, very complex ecosystem, or the very, very complex system. Just to think about one individual, how complex it is. And ecosystem means several 100,000 individuals and their interaction. So just to think about the complexity. He described all these things, the Janus hypothesis, ecological synergism, and the theoretical aspect, and he related the theoretical aspects with the empirical aspects, everything. And I'm really thankful to him because he described the Janus hypothesis in such a good way that people can relate all these things with the Janus hypothesis. And one thing I'm telling you, Adam Smith, I'm also very fond of Adam Smith, he's a great economist. And everywhere some individual hand is required, because this is the, this is the quote of the Adam Smith. And particularly, so for the complexity of the ecosystem is concerned, without any invisible hand, I think the system will not be in order. And whatever the situation we are facing, these are typically disordered system due to lockdown, due to some fear and other things. And I think so, the individual hand is there, and that individual hand can actually surpass the winter period. So far, he told about that the crypto economy or the cryptocurrency. So I think we'll be over within a short period of that particular phase, the frozen phase, and we'll see the new sunrise, and the world will be in order. And one thing I'm telling you, particularly Professor Patton, I can see. So science and philosophy, two things, it is very difficult to relate two things. And he is the person, he can move from science to the door of philosophy and enter the philosophical room. And he describes so beautifully the philosophical aspect, the theoretical aspects. Without any philosophy, you cannot explain the theoretical aspect. He is the particular person, he can describe the the scientific things with the help of philosophy, and where science ends, the philosophy starts. And like this particular people, the people of this stature, they can actually enter the philosophical world, and they can relate the philosophy with the science. And we are very, very thankful to Professor Patton. And I think so we will hear many more lectures of Professor Patton, and I will be very, very thankful if he again comes to India whenever the situation will be normal. And I'm welcoming Professor Patton to come here again, and we'll arrange everything for you, and we'll enjoy your lecture. And I think everybody enjoyed your lecture. And one thing I'm telling, another thing, particularly there, whatever the audiences are concerned, not all are for the ecological field. There are many from other biological field, particularly the cellular biology or rather the molecular biology. One thing I can say like that, that is the network environment analysis, whatever he told about that, that can be applied not only in ecology, it can be applied to the cellular biology. You think about the biodiversity. So here, the different types of cells, or the cells, there are a lot of complexity, all the cells having different autonomy, and even there are the beautiful connectiveness between the cells. So if you think in that way, the cellular biology with the ecology, the same tool can be applied to the cellular biology. And I think so, the young people, there are many, many young people, young students, they can apply these um, uh, network environment analysis in the cellular biology or molecular biology, and I
In
think
fact,
people will enjoy.
there is
So
one
thank you
question,
again.
Shantanuda. Right on cue. No, you stay here. Right on cue, there is a question from the audience. Oshim Chakraborty asks, do you think your hypothesis may be applicable in reduction of cancer cases in the future? Professor Patel.
That's a real jump, isn't it? I think networks are fundamental. And in an organism, complex organisms, which means every organism, even a cell, networks are operating, but that is not the way we know organisms. We know the brain, the human brain, a little bit that way. I think network science, and there are organizations now becoming devoted to this. I think network science is going to grow in the future. When I was watching the video, I was reminded of the radio ecology experience. Put a radionuclide anywhere in an organism, in an environment, and it spreads quickly. The network is a central part of all of us. Cancer is ultimately will be seen as a network problem, probably. I suspect its solutions will come in the genetic realm early on, or in the pharmacological realm. So, will the hypothesis be applicable in the reduction of cancer cases in the future? I don't have a good sense of that. Okay. But if cancer can be represented as networks, then I think things go from there. And my core idea is, I'm not an applier. I'm finding that out in this cyberscript experience. It's not my role to try to apply things. And I've said this at the beginning of my paper. I'm presenting ideas as a scientist, and but better people who know the realities. You know the saying, the devil is in the details. People who know the realities can take the core idea of bridging. It's just that, like the cardiopulmonary bypass surgery, which I use as an example, to take those things and begin to apply them. I cannot, but I can give the broad ideas and develop the broad idea. And that's what I'm trying to do now. And there's a lot of naivety there, and frankly, I've had a problem getting this out. I invite you to do two things. You have the video, you can distribute that as widely as you wish, please. And secondly, you have the manuscript, and probably more coming from me as I proceed with this, because it may take a book form, but right now I'm trying to work on a short form that can be distributed to people who have knowledge. If you can take this cryptocurrency thing and apply it in India, that might be a really, really good thing.
I was thinking that maybe Shantanu and I could take these questions, and as days progress and you have a better insight into the concept that you have been developing, and we can actually have a brainstorming session with people from different disciplines, because as I understand, the concepts are very empirical, and as it applies to the ecosystem, it also applies to other things such as economy, and such as the way state develops or crumbles, like you just mentioned. India right now is also going through a major crisis, both in terms of economy. We have a farmers' movement building. There are numerous issues, as I'm sure other countries in the world are also grappling with. So these are unprecedented changes in the social framework as well. And I have every confidence that the model that you are talking about and that has played out in the nature applies equally to them, factoring in other things, of course. So with that, we thank Professor Patel for a wonderful lecture. I mean, wonderful doesn't even describe our feelings. So it is an honor and privilege to have been able to host you, and I hope we will be able to take the idea forward. And our heartfelt thanks also to Professor Shantanu Rai to come here and take part in the proceedings. Thank you to our audience who will doubtless tune in later, because it is kind of late in the night in India. So I'm sure they will be logging in, and we have people logging in virtually from all the continents. So they will be doing it in their good time. And we will share our email address in the YouTube link, and or they could also go to the website of Progress and Prospects in Biology, and they can send us questions, because this is a very, very interesting field of study. And as Professor Rai said, Not many students of biology would be very conversant with the mathematics part of it. And so this is something very interesting. I think in the next week, Professor Rai himself is going to give a talk, and we will learn more about it. So with that, we end tonight's session. Good night to people in India and this side of the globe, and have a very nice day to Professor Patton, who took time to share his insights with us. And with that, we conclude tonight's session. Thank you so much.
Thank you. Good night. Bye.